Let us look at how the Laplace transform can solve the wave equation on a semi-infinite domain. Picture a very long string or rod that only exists for x greater than 0. The wave equation says the second derivative of u with respect to t twice equals c squared times the second derivative of u with respect to x twice. At the near end, x equals 0. The motion is prescribed and given by some function f of t. Far away, as x goes to infinity, the disturbance must die out, so u stays bounded there. We also assume the string starts perfectly still, so both u and its first time derivative are 0 at time 0. The first step is to take the Laplace transform in the time variable t. We define capital U of x and s as the integral from 0 to infinity of u of xt times e to the minus st dt. Here s is just the transform parameter, and x is still an ordinary variable. Applying this transform to both sides of the wave equation turns time derivatives into multiplications by s. Because the initial displacement and initial velocity are both 0, the transformed equation simplifies to s squared times capital U equals c squared times the second derivative of capital U with respect to x twice. Rearranging gives an ordinary differential equation in x alone, with s sitting as a fixed parameter. In words, the second derivative of capital U with respect to x twice minus the quantity s squared divided by c squared times capital U equals 0. This is a simple constant coefficient ordinary differential equation, and its general solution is a combination of two exponentials. In words, capital U of x and s equals a times e to the minus x times s divided by c plus b times e to the plus x times s divided by c. Now think about what happens as x grows very large. The second term, with the positive exponent, would grow without bound, which cannot represent a physical wave that stays finite far from the source. So we discard that growing term completely, meaning we set b equal to 0. That leaves only the decaying exponential piece, capital U of x and s equals a times e to the minus x times s divided by c. To find a, we use the boundary condition at x equals 0, where capital U of 0 and s must equal capital F of s, the Laplace transform of the boundary motion f of t. This tells us a equals capital F of s. So the full transformed solution is capital U of x and s equals capital F of s times e to the minus x times s divided by c. Now we invert this transform back into the time domain. The key fact we use is the time shift property, which says that the inverse Laplace transform of e to the minus as times capital F of s equals f of t minus a times the Heaviside step function evaluated at t minus a. Here, the shift amount a is exactly x divided by c. Applying this property gives the final solution, u of x and t equals f of t minus x divided by c times the Heaviside step function evaluated at t minus x divided by c. In plain words, the disturbance at position x is simply the original boundary motion, delayed by the travel time, distance divided by wave speed. Let us check this makes physical sense. Pick any fixed point x that is greater than 0, so it sits away from the boundary. For times t less than x divided by c, the Heaviside function is 0, so u of x and t is exactly 0, meaning nothing has happened yet. Once t exceeds x divided by c, the Heaviside function switches on, and u of x and t exactly reproduces the boundary motion, delayed by that travel time. This matches our physical expectation perfectly, since no disturbance can reach a distant point before enough time has passed for it to travel there at speed c.